All right, let's start talking about rotations. Where this is, what we're basically doing is kind of starting back from scratch, where we initially looked at displacements, velocities, and accelerations, right? Well, that was for things that were translating. So we could have a mass here at some time, and then everything moved without rotating, right? Just a translation to some new location at 2. To fully study what's called general planar motion, we would have to include a rotation too, because that object might be translating through space, but it could be rotating as well. And we'll see it could rotate with some angular velocity omega or some angular acceleration alpha. And I'm going to derive those for you. But we're going to start by looking at the units of measurement and stuff. So just like we started out this whole entire first lesson of the semester, we were just looking at position coordinates in x, y, and z space. Now we're going to talk about when something rotates, it sweeps through some angle theta. So we're going to talk about the units. We're going to talk about the time derivatives, which are the angular velocity and the angular acceleration. We'll define everything regarding how to use the kinematic equations. They're actually very analogous and look just like the other ones from before. And then we'll start looking at moments of inertia, because when something rotates, it also carries with it energy. So a golf ball that's spinning while traveling through the air has more energy than one that is just traveling through the air at that same speed without spinning. Something that rotates and has mass also carries momentum with it. That's where we're headed. I've also mentioned that we've been saying so far, we look at a mass center, any forces acting on the body, we're going right through that mass center always. Well, what we're going to lead up to is that since things can rotate, well, forces don't have to be applied through the mass center, and that causes what's called the torque, and it'll rotate. So that's what this unit's about. In my ME242 class, I spend probably about a third of the semester on this, because we study, just like we have been, just in more depth. We study the translating motion of particles, then we start looking into systems, and then we look at what happens if they're rotating, because most things do both. Okay, so took this one from the book just to give us a good diagram to work with. This is some solid body, so it's got some mass distribution, most likely uniform. We'll learn that depending about what axis we rotate it about, in this case we're rotating it about the z-axis. Notice this arrow. And in this is also would be considered a positive rotation. So if we go from x up towards noon, or towards the y-axis, that is a positive rotation. So let's start defining some of this stuff. Let's take this blob that we're just looking at, and this is y and this is x. It's rotating about this axis right here. Get rid of that for now, but let's say that we want to look at some point on the object. Let's just put some point P on here. We could locate that with a vector. And we're not going to actually get into vectors too much in this, but I want it to be noted, all of this can be done very properly with vectors. we're only going to spend a few days on rotations, but just know that, and I'll point out the definitions when I get to them. A lot of these actual definitions will come from cross products, and we're just going to basically bypass that and do some multiply the angular velocity times the radius will give us velocity. So like stuff like that. That's actually going to be omega crossed r is equal to the velocity. Anyways, so we have this mass here, and we're locating some point P, and I said I got on the vector thing because we should locate it with a vector r. But we can just say that for now it is just some radius. And it's any point, or that point, if going about this axis, is going to take a circular path. So along this radius from the center would take a circular path. Alright, so that's the path of that point P. So if it moves to some other location, so maybe this is the vector locating it at some initial time, that point P will move over to some new location. And what it did is sweep through some angle theta. So that's what we're looking at now. We're looking at the angular units. And theta and the radius r are going to be of the most interest to us. If we want to describe the angular position of something, we can use the fact that the arc length, that theta is equal to the arc length it traveled over r. That's just a little geometry definition. We're going to use that to derive some of our other equations, though. And I'm going to say this as many times as I can remember. Whenever we're doing theta anywhere in this, theta, I'll go ahead and say it now even though I haven't really introduced it, omega or alpha, they need to be in radian units. Don't forget that. Your calculation will not come out correct unless your angle theta or your angular velocity is in radians or radians per second. It cannot be in degrees per second. It won't work. So to solve that, what we can do is say, well, if something goes around one time, that's one revolution. You know what that is. You've heard that before. And if it goes all the way around a circle, we know that one rev then is equal to 360 degrees. Well, we also know that that's equal to 2 pi radians, right? We have pi over 2, pi, 3 pi over 2, and then back around to 2 pi. So we can use this to calculate from one to another, where if you don't remember, if we take a unit circle, close enough. Alright, if we take a unit circle, and this would be our radius right here. If we take that and lay it down along the edge of the circle, and then draw a line to this point, and measure this angle, that's equal to 1 radian. And it's about 57.3 degrees. Should honestly kind of try to remember that. If you keep doing this, do one more radian, another radian, another radian, and then 1, 2, 3, 4, 5. You end up with 6 pi slices, or 1 radian, times 6, and then a little bit extra, ends up being about 0.28. And guess what? That's 2 pi, or 2 times 3.14. It went 6.28 radians around. So 6.28 radians is approximately equal to 2 pi radians. That's what I'm getting at. There's 6.28 pi slices to get around the circle one time. That's how I remember it. Okay, now let's go back up here. Let's make a new one. If we try to put this at the center, there we go. If we look at some point P and it moves to some point P prime, it initially had some angle theta. We can call this theta 1. And then it moved along its circular path, right? This is uniform circular motion stuff, so it's a circular path. And we can draw another line to it and measure that degree measure from the same axes, the positive x-axis. And we measure that as theta 2. What we get is delta theta, or the change in the angle theta, or the angular displacement. So before we talked about displacement, delta x is equal to x final minus x initial, or x2 minus x1. Well, guess what? We got theta 2 minus theta 1. So that's your first definition. And it might be intuitive to know what we're doing next. If some time went by as it moved from point 1 to point 2, and we know its initial and final angular position, we take that change in position, divide it by time, and we end up with what's called the angular velocity. And that's going to be denoted with an omega, and this will be our average angular velocity definition. So basically theta 2 minus theta 1 over t2 minus t1. That tells us it's a measure of how fast something is spinning. We're rotating now instead of moving in a straight line. Okay, now guess what we can do? We can take the limit definition and say the instantaneous angular velocity would be the limit of, as delta t goes to 0, of delta theta over delta t, and we get d theta dt. That means if we have theta as a function of time, we can take its derivative. Omega is going to be equal to d theta dt. And I'll do an example where we do that. Just like before, if we had the x position as a function of time, x was equal to maybe 3t squared, we could take the derivative and get to the velocity, where velocity is equal to dx dt. That's the same thing. And we can take it one step further. Taking it one step further gives us what's called alpha, or the angular acceleration. And our average definition would be the change in angular velocity over the change in time. So we'd have omega 2, or the angular velocity at 2, minus the angular velocity at 1, divided by t2 minus t1. Now, just like acceleration, this gives us a measure of its angular acceleration. How fast did it have to speed up to while it was going from point 1 to point 2? It was speeding up, right? Okay, the limit definition then gives us the instantaneous angular acceleration as d omega dt. So both these are all important definitions right here. Okay. So do an example real quick. What if we're given, this one's in your book too, the sample problem 10.02. What if we're given theta? What if we're given alpha as a function of time? So the angular acceleration, and it's equal to 5t to the third power minus 4t. So we're doing the same thing that we did before. This was just x or y or z before. Now it is, I'm sorry, before it was the acceleration in the x, or the acceleration in the y, or the acceleration in the z. Now we're looking at the rotational acceleration, or the angular acceleration. What we can do is take this definition right here and separate the variables. So if we have alpha is equal to d omega dt, we can put the dt on the other side, say d omega is equal to alpha dt. And we're given alpha, so we can go ahead and plug that in. 5t to the third minus 4t, not squared, minus 4t dt. Well, guess what? We can integrate this whole thing. Integrating it will give us 5/4 t to the fourth minus 4 over 2, t squared, and then we get a constant. And you can actually integrate from omega 1 to omega 2 if you want, and from t1 to t2, and figure it out that way, or you can go about it the way with the constant. The book does it this way, so I'm going to go with this. Once we get, if you get to dynamics class with me, if you're an engineer, then we'll be integrating with variables like this. If you know t is equal to 0, go ahead and throw that in. If you know what time you're interested in, go ahead and throw that in. And in this problem, let's say we want to know what's the angular velocity, well, as a function of time. That's what we just found right here. Boom. If we say, let's give it some initial conditions, make it an actual problem. Let's say at time is equal to 0, the angular velocity, or omega, is equal to 5 radians per second. What we can do later is, with this information, is find omega at any time t. So you could actually put omega right there if you want, and t right there, and we don't have to worry about the constant of integration right here. Or you can just go ahead and substitute them in right into this equation. It doesn't matter, whatever you're more comfortable with. So if we do that, we would put we need a theta. We'll use that in a second. We're going to look at we're going to take it one step further and look at the angular displacement also, and we'll need to know the initial condition, that theta is at 2 radians. Okay, box those for now. Initial conditions. What we can do is say that to have 5 radians per second. Substitute these into this equation here. These with evaluated at t is equal to 0, just turn to 0. And we get the constant c and our final angular velocity expression. 5/4 t to the 4th. This reduces down to just a 2t squared, and then we know the constant now. So you could have gone about this with putting the integration variables in also. Alright, now what if we wanted to find an expression for the angular position? We want theta as a function of time now. Well, if omega right here is a function of time, we can use the definition that omega is equal to d theta dt. Break that up into d theta is equal to omega dt, and let's substitute this expression in for omega. So d theta is equal to 5/4 t to the 4th minus 2t squared plus 5 dt. Then we can integrate it. And if you're looking for the final position, you could integrate it to the variable, but you'd have to know the initial, which we do. We have the initial angular position as theta is equal to 2 radians. But we're going to find a general expression for this. Any time t expression. Okay, so evaluating at theta is equal to 2 and t is equal to 0. Integrating first actually gives us theta as a function of time. And then we'll evaluate. We get 1/4 t to the 4th minus 2/3 t to the 3rd plus 5t plus that constant c. So plug this in, plug that in, we can find out the constant is equal to 2. And our final expression for any time t would be this right here. You want to know what angular position it is at 2.9 seconds, just plug in t. Okay. And the book talks about, are these vectors? They are. Angular displacement is, the angular velocity is, the angular acceleration is. They do have vector signs over them, and I'll talk about it more when we get into some more of our kinematic stuff, but we can do this for any vector r in 3D space with a line of rotation with some omega on any axis, and same with alpha. Just be prepared that they are vectors, and you will possibly be referring to them as vectors in your future depending on the route y'all take. We're going to simplify it pretty much that we're just going to denote it with a plus or minus sign, where positive is going to be rotating from the x-axis, whether that is omega, theta, or alpha, and negative would be in the clockwise direction. Alright.